Our first speaker is Nigel Charman of Rolls-Royce. He's been in the aerospace and software industry since the mid-1980s, first working on Seawolf, Ariane 4 and Tornado programs before joining Rolls-Royce, where he's worked on small civil, large civil and marine gas turbines. He has tested the software and electronics on missiles, rockets, ships and aircraft, and can remember CPM 86 and OS2, and now leads the testing of DSPs and the adoption of behaviour-driven development. And I'm going to welcome our first speaker, Nigel, who's going to speak on intelligent testing in complex environments.
What are we going to talk about? We're going to talk about the intelligent testing of complex systems, and I'm going to press a button and see what happens. Oh, marvellous. Right. So, you go off on holiday, and you walk out across the airfield, and you get to the ramps, and just as you go into the aircraft, you go past the engines, and you have a look at a big engine there. And is one of the first things you think, by God, I hope the software doesn't fail on that. yeah, me too. No, you generally don't, do you? You don't even really think about the software in these engines. With a mobile phone, you might get it and put some new apps on and go, oh, that one crashed, that one didn't. Something as important as that, we can't afford to have people getting on thinking, software doesn't often work, does it? You know, sometimes it just fails, the whole system crashes. We want people to think, I've never heard of that. I've never heard of the software on an engine or an aircraft crashing. You hear about things like geese going in the engine or things like that, and you know the software world can't do a great deal about that. But we want people to be not only utterly confident, to have every reason to be utterly confident. Now, people are nervous about flying. It's understandable. You're in a long tube and you can't see out. But what can we do with a complex system to make sure that one of those worries just is not a reality? Yeah, this is a story. A friend of mine was on a plane, and the chap next to him complained that 75 quid was far too much. He said, we're going all the way across to Dublin. He said, what a waste of money, 75 quid. And the colleague said, so what do you do? He says, well, I'm a farmer. And he said, oh, yeah. And he said, you've got a big tractor? He says, oh, yeah, huge tractor, one of the best. Cost $500,000, whatever it was, £300,000, you know, huge engine. He says, could it tow 300 tons? He said, well, I can't do that. He said, oh, what could it tow? He said, oh, I don't know, about 30 tons maybe. He said, what do you have to do to get it to tow 300 tons? He said, oh, it'd have to be pretty big, complex engines and four-wheel drive systems and braking and everything. He said, what about towing 300 tons to 175 miles an hour? Said, no, I can't do that. So what about getting to 175 miles an hour in 21 seconds? Said, no, I couldn't really do that. He said, what about once you get to 175 miles an hour, hitting the bottom of a hill and climbing to 2,000 feet in another 40 seconds, whilst accelerating? And he said, oh, I'd have to be a hell of a tractor to manage that. And he said, and then climbing on to 10,000 feet and 30,000 feet and hitting a top speed of 500 miles an hour, towing your 300 tons. And he went, no, you've got me there. And he said, temperatures in the same journey from plus 50 to minus 60 maybe. He went, oh, yeah. So what do you reckon a tractor like that would cost? He said, oh, millions, tens of millions. He said, would you rent it out for 75 quid a go? Said, no, I don't think we can do that. And people take for granted the complexity and the technology going into these. And a lot of this is mechanical, of course. The mechanical side of the engine is very, very important. But controlling that and making sure that everything is within tolerances, is spinning smoothly, is reliable, is the software. Wrong button. Okay, Bill Gates apparently said there's probably no development in the world as complex as the development of a civil jet engine. He didn't say it to me, but I heard that he did say it. And much of the safety, much of the reliability is in the software, is in making sure that all of the hardware is operating within the limits of what it can manage. It doesn't get too hot, it doesn't spin too fast. Where you've got a couple of signals, you're selecting the right one. Where you've got electrical failures, you're ignoring them, you're coping with them, you're managing them. So the overall complexity of a gas turbine control system is large. And safety is the #1 priority. And that isn't just a slogan. We make them cheap, but occasionally they drop out of the sky. You know, they're not like mobile phones. You're not going to say, yeah, fair enough, but it was good value. you're not going to fly. You're certainly not going to fly with Rolls-Royce engines. So we have to make sure they're safe. They continue to work all the time. We can't have a blue screen of death on an engine against it. Pilot says we'll be rebooting, we'll be landing in 5 minutes. So we have to test the software. And how does testing help us achieve this? Pretty stupid question, really, isn't it? We have to have total control of what's going on in the computer and in the engine. We have to have control of the software design, the implementation, and we have to have total control of the testing. It can't be an afterthought. We can't produce the software, get the engine running on the test beds and sort of say, yeah, we're pretty much ready to stick it on an aircraft now. Now we'll just have a go at testing it and make sure it's really okay. We have to test it from the beginning, and it has to be thorough. So all the software has to be tested. It has to be effective. So every function that's required of the engine that has software involvement has to be tested. Every failure case, every broken wire that might mess up an input, every possible combination that can happen have to be tested. It has to be affordable, otherwise we can't compete with GE. GE are our big competitors, GE and Pratt & Whitney. And if they can knock £10 million off a program, they can knock an equivalent amount of cost off the first few engines, and then we can't compete. And it has to be achievable. Unfortunately, when an aircraft manufacturer declares a new program, so Airbus declare their new A370 or something, they're going to have got orders from the airlines. They're going to know pretty much what they want to do, when they want to do it, and we will get involved, and they will be told, we'll be involved in the planning stage. We'll be told, this is the new airliner, this is the size of it, this is the size of engines we want from you, and the first customer flight will be on this date. The first flight of our flight test will be on that date. Customers are already committed. There are people out there who maybe would have gone and bought a 787 and they said, no, we trust you, we're going to buy your new Airbus, or the other way around if it's a Boeing. So we don't really have many options for being late either. And also, we have total responsibility for all of our suppliers and supplied components. So the hardware it's sitting on, the sensors that link into it, all of those components are going to be part of the engine, and it's not going to be much of an excuse for us to say, well, yeah, the software did go wrong, but that's because this sensor collapsed internally and it just gave silly values. It's nothing to do with us. Go and see the sensor manufacturer. We're delivering the engine, and you expect the whole engine to work. So we're talking about electronic engine controllers. What does a controller do, really? Fundamentally, a gas turbine is really simple. You've got a number of shafts. Let's start with the middle one. You've got an intermediate shaft. It compresses the air right down. It injects fuel. It ignites it, and it puts it out through a turbine. They're on one shaft. So as the turbine gets the air coming out, it drives the compressor. And when Frank Whittle put the first one together, he didn't really know whether it would even be self-sustaining, whether you could get enough power out of the back end to drive the compressor. And they started it, and it went so fast, apparently they all ran out of the buildings with their heads between their hands, expecting it to explode. It generates a lot of power. Rolls-Royce have 3 shafts. So we have a high-pressure shaft. Running through the middle of that, we have another shaft with a low-pressure stage, an intermediate pressure stage, and running through the middle of that, we have the low pressure, which has the fan on the front. They're not physically connected. They're just driven by the gas flow through there. So the first thing we do, effectively, is we control the fuel flow. This is running all the time. The amount of fuel going in there determines how fast the engine goes, how much power it produces. That one's nice and simple. We have stator vanes that can control some of the airflow. They're variable stator vanes. We can change the angle for low running and high-speed running. We have to look after those. We have to switch the igniters on at the beginning to get it going. That's basically it. It's easy, really. That's what all the fuss is about. That's how you hop on. We control the fuel flow. It gives him some thrust. We measure some pressures. We measure some temperatures. We measure some speeds. And we put that out on some sort of a bus system these days to the cockpit. It's not hardwired. And he can see what's going on. So that's not too tricky either. We do have tricky things like reverse thrust. You've got to land and stop. Passengers do appreciate it if you stop before you ask them to get off. Otherwise it's really hard running along with your suitcases as you go down the ramp. And then we've got lots of other little bits. Fuel efficiency, very, very important. You're not going to manage a 75 quid flight if we're chucking fuel through there like nobody's business. How do we get fuel efficiency? We run at really high temperatures. We run, in fact, at such high temperatures that these parts of the turbine back here are running in a gas higher than the melting point of the metal, which they achieve by blowing cold air through the blades and out so that there's a cooling layer over the turbine blades. We monitor that. We monitor that temperature very closely. And that'll be on one of these dials. Perhaps this one, 350. That's quite low, but there you go. We'll give warnings if the temperature gets too high. The temperature can get too high if there's damage on the engine, it's not running very well, you can get temperatures that are too high. We'll give warnings. Ultimately, we'll limit the fuel. We'll bring that back down. We have to manage the speeds. If it spins too fast, obviously, it stresses the engine. So again, we have to do all of that. We look after fuel flows, we look after temperatures, we look after the oil system, we look after vibration, we've got electrical generation on here, pumps. You can see the complexity starts to build up. On any one of those, we have to be able to manage electrical faults, short circuits, open circuits, dual sensors, comparing the sensors, which one's right, which one's wrong, which set of control laws are we running on, which sensors do we need for those control laws. So it starts to build up. From our airframer, we'll get a set of requirements. This is what we want from you. There's lots of mechanical requirements in that, but from the software world, they will tend to be control laws, they will tend to be behaviours, they'll tend to be interface specs, how do we talk to the cockpit, what sort of data do we want to send, how do they want to start the engines, how do they want to run it, what sequences of switches are coming through. But a lot of it they leave to us. We run the engine, we just provide the thrust and push it along. That comes down. We will then have engine requirements. What do we need to do with the engine? What are these limits, these temperatures? What is a starting sequence? What's an acceptable level of vibration? Does it change? One of the things that we're doing with health monitoring now, looking at the vibration, and by having, we measure speeds with a toothed wheel and a magnetic probe. If you have a missing tooth, you take one out deliberately, you can tell where you are in each rotation. And if you can correlate the vibration with the position to get a phase, you can work out whether the engine is out of balance, and if it's out of balance, where it's out of balance, and then they can put balancing weights on because of the calculations you can do. So you can say, actually, this engine with a little bit of degradation has just gone slightly out of balance, and put a small weight there and it'll be back in balance. So we can do that sort of useful information. They come down as engine requirements. They'll flow down to EC, the engine controller requirements, which will then split into hardware. We need a box, it's got to be so big, it's got to be able to cope with 50 degrees or more. I was on a flight test campaign in Tunisia, and the outside temperature is about 50 degrees, and we had to do a full throttle takeoff, fully loaded, all simulating a maximum amount of fuel and passengers, and then just as you get down to the end of the runway and you've rotated, change your mind, put the front wheels down, come to a halt, and then just sit there. And we saw something like nearly 100 degrees under the cowling then. We also had a black cowling. We had to paint that one black specially, because you never know what colours an airline's going to want. They may want black aircraft. So that's the hardware requirements. And then on the other side we've got the software requirements. But we've gone down through control laws. What does the software have to do? What are all the signals? We've got the order of 600 cables going into an EEC. They're not 600 signals. Some signals are maybe 5 wires, some 4, 3, 2, but a lot of signals, a lot of possibility for wiring and data problems, and then down to software functions. And it's lovely. It's a nice, easy set of structured requirements. Of course it isn't. That's what it really looks like. And worse, you've got airframe requirements on the software. They want to make you do certain things. They want direct bus communications. They don't pass the bus through the engine. They go directly to the software. You've got regulatory requirements. How do you have to do stuff? How do you have to prove it? How do you have to test it? We've got maintenance requirements. How are we going to be able to look after this in the future? What sort of data do the ground crew want when things happen? The hardware supplier, we're going to come back and say, can't do that. We want you to put something in the software to manage it instead because that's too tricky. All the sensors and actuators, they want the software to behave in a different way. So it gets quite complicated. And at the end of that, we've got to test it. So that's where we are. You've been given this project, large number of signals. First date is committed. The engine fuel consumption must be superb, so we're going to have to operate in tighter tolerances than ever before, and the overall cost is fairly well committed. So we can't really afford to go around the testing loop a lot of times. We've made sure the program is well planned. We've got enough money to do it, but only do it once, 1.5 times. So, in the purest sense, software testing is sort of up to here, up to when you put it on the target. To Rolls-Royce and to the airframe manufacturer, the software testing is delivering a box that works. So they're not really thinking about just the software. We can't turn around and say, well, the software was fine, there's some sort of stack overflow, and that was a hardware problem, really. They don't really care about that. The engine stopped, did the wrong thing. So hardware testing is effectively an important part of software testing. Can we run it on the hardware? Does it behave correctly? Do the electronics in the hardware feed the right signals into the software? This sort of counts as software testing in many ways because the two are so closely coupled. We would then go on to system testing. If we put a box like that in a representative environment with simulators, does the software functionally do what's needed? Maybe super bit of software, it may never crash, it may have not used much memory at all, and be beautifully architected, but if it doesn't do what's needed, if it doesn't control the speeds accurately, if you haven't got the right information coming out, if it doesn't generate the right messages, it's fairly useless. We'll then go on to engine testing. Testing on a rig's lovely, but guess who specified these rigs? Well, the control system team did. And guess what assumptions they based it on? Well, they based it on their understanding of the engine and the environment. And sometimes we get that completely wrong. So we think we've got the requirements coming down, we flow them down, we build a rig to match the requirements, it goes on the real engine, and it's absolutely nothing like that. Usually silly things, little details. I remember one where the airframe was going to provide 24 volts. It would come in, we'd read it, and then on the outside it would either switch that open circuit or to ground so we could detect the 24 volts. So we built that in, beautiful, all working, put it on the aircraft, on the engine, didn't work at all. In fact, it was after engine testing, it was when it went to the aircraft. With engine testing you don't have all the thrust reversers and aircraft side. And it was a simple problem, 24 volts, switch to ground. They'd done them that way around. So as far as they're concerned, it was a simple in-out, and we just made a wrong assumption and got them the wrong way around. So where we were trying to measure the voltage on the output side, it was just staying at 24 volts all the time. So, silly mistake, but you have to go through the whole sequence in order to find out. And that was effectively a software fault. We had a voltage monitor on either end and we read the wrong one. So, that's effectively a validation V, wasn't it? Understanding the customer requirements, deriving the requirements, evolving a system architecture, specifying software requirements, architecting a software system, designing software components, and then implementing them, testing them, unit testing, integration software, integrating the software with the target hardware. You see we're still calling develop and verify software. Is it running in the box? Integrate the system. Is the box running with representative sensors? Verify, sorry, integrate as a system, yeah, get it running in the box. Verify as a system, and then customer acceptance. So this is going on our rigs, on engine test, on flight test. So, yes. Okay. We normally refer to verify as effectively being the same as test, and validate. So we validate requirements by proving that we've got the right requirement, going off and understanding the functionality that's needed, and does that requirement represent what's needed, and verify, have we done what that requirement requests us to do. So test, in this case, I'm using to mean the same thing as verify. Yeah, yeah. So most of our requirements aren't complex, but we've got lots of them. So we have to divide and conquer. We have to test them at a suitable level, but we also have to have the ability to pass them up or down. You may not be able to test something on a rig. You may have to pass it to flight test, or you may say, actually, we can't generate this fault in flight or on a real engine. It's just too difficult. We can only test it in software. We'll have to pass that down. We want to test things as low as possible. Testing at a higher level is expensive. On the other hand, testing at the higher level on the plane is the most realistic. So we have to balance those out. We need to track the results passed up or down, and we need to track results tested across multiple vehicles. We want to test things a few times, but we don't want to test them too many times. We don't want the same test run over and over and over. So we'd have a, let's say this is a modification to a main build. We'd have an IP, an implementation plan, what the problems are that we're going to fix. We'd have changed requirements. These are maybe requirement documents, one on thrust reverser, one on something else. That would produce a whole load of what we call tags, individual requirements. You know, when this temperature is greater than 6, light the light. We then split that up into tests covering functional areas, and each of these tests will cover one or more requirements. You may have to have a number of tests to test a requirement. It may say under all circumstances do this, and we may have to have 20 tests doing it. Or we may have one test, maybe doing an engine start, that can cover 20 requirements. So there's a many-to-many relationship there. And then these tests will have to be allocated to vehicles. Where's the best place to do that? So an example, when a temperature exceeds a limit, generate a message in the cockpit. That's a nice system requirement. We get our hardware that our supplier has validated will do this. It will take those inputs, those millivolt inputs, analog to digital, and will provide us a signal. So we've got their test results. That's part of our result, our test case. That'll go in through our OS. Our OS will look at it and say, this sort of A to D signal that we've got, is that a reasonable number? Does it say it's 8 trillion degrees? If so, probably the sensor's failed. It's producing a millivolts, but it's rubbish. So it'll validate the signals coming from the hardware. It'll pass it to the application software. The application software will say, all right, we know the temperature's between 0 and 100. That's great. What should it be? The engine's running like this. It shouldn't be above 60. Bit of a problem. Fault handling. Temperature's above 60, but we know it's genuine. Therefore, something's gone wrong with the engine. Pass a sort of a fault off, saying there's something gone wrong with the engine. Alternatively, one sensor says 80 and one says 30. Now what are we going to do? We've got two sensors supposedly measuring the same thing. So we have to have fault accommodation logic. We would generally take the worst case. If they're in range and one of them's high, that's generally the one we would go with, assume the worst. We then have to do something with it, generate messages, handle the engine in a different way, pull the throttle back, close a valve, do some cooling, something like that. We'll then have to output on maybe AFDX, if it's Airbus, the bus system, some messages out to the cockpit, and maybe we'll have to handle the engine differently. So lots of different stages, many of these deeply software. So splitting it down quickly and going through the stages, because I'm beginning to run out of time. We've got our hardware. We know that the software runs consistently on the hardware. That's very important. The box must never crash. The hardware itself must run consistently. When it's hot, when it's suffering vibration, when there's EMC, when we've got internal faults, the box must be able to detect them, flag them, isolate them. So we know what's going on is consistent. We then do software code level testing. We will do formal methods. the sort of thing like Jim was talking about earlier on just before lunch. We need to know that all of the code is executed, there's no dead code, all the decisions can be exercised, that there are no divide by zero type errors, overrun errors, the software itself is not going to crash. And then functionally, each of those units does what's required. So we will have a unit spec, we will check what, we'll have a load of test cases, what data should go in, what results should come out. They're generally simple things. The functions are generally divided down so that each one is as simple as possible. This is a simple range check on a number, or it's a select highest wins type of little block of software. We can then integrate those together into the software and with the operating system. Often we'll just run that single lane. That's a sort of a combination of software integration and a bit of functional operation. It's some limited realism, so we wouldn't have necessarily all the three shafts showing real numbers that are representative of an engine. We may just be exercising one up and down and then another one. And we would want the ability to perform deep inspection and actually insert fault numbers and spurious numbers into the software at that stage. We would then put the software onto the real hardware and run it on real-time rigs. So it will be getting its 600 odd wires exercised as if it's attached to a real engine. There we'll tend to run real representative test cases, starting the engine, shutting the engine down, but also wiring faults, pulling them out, shorting them. So does the software, when sitting on the real hardware as a system, do what you expect? And sometimes it doesn't. Sometimes with the best of intentions, we'd expect to detect an open circuit. The hardware says it can do it, the software says it can do it, put it on the rigs, it can't. Various reasons for that we have to trace back through. Then do system testing. And this is real end-to-end. This is maybe with a cockpit simulator. If they generate the right cockpit signals through to us, do we do the right things? Do we send the right AFDX messages out? This is the point where we sort of start moving into black box testing area. We're not looking inside the box so much. We're treating it as a system. For the moment something goes wrong, we want the ability to look inside the box to try and work out what's gone wrong. With this we can test areas that the engine can't test. So multiple overspeeds, multiple failure cases, all sorts of things. Engine test. Real hardware on a real engine in a test environment. More limited still. There's less we can do with this because we don't want to blow them up too often. They do get upset about that. And it's expensive, £5,000 to £10,000 an hour by the time you've got one of those and all the blokes associated and the fuel. And those test engines are being developed as well. They're trying new turbines, valves, sensors, all sorts of things. And quite possibly passing off production engines. So we may get a fairly limited slot and we've got to use it effectively. We'll then go to flight test. Again, fairly limited. The airframer has got their aircraft, they know what they want to do with it. And we get to do some stuff on there. We have to prove stuff to the airframer, and for certification, very often, I mean, I was on the A340, we're sitting in them, in which case we're doing really limited tests, okay? Keep it nice and simple. It's all been done on the engine, I'm fine. And then we have to gather all those results, and we have to collate them. And we have to produce result reports. Now obviously, whenever we've come across a failed test, we'll have been feeding that back as early as possible to get stuff fixed. But we typically have 3,500 to 5,000 requirements altogether, and they're going across a range of tests, so we could end up with multiple thousands of results easily. And they have to be all pulled together. And the difficulty with some of this is some of these requirements will have many, many tests, and some of them will only have one or two. So if you've got 99 passes, is that everything? Or was there another test somewhere else that hasn't run yet, but you got another result? So we've got multiple vehicles, multiple levels of requirement. From the airframer, we have to validate we're meeting those. The engine requirements, we've got to validate we're meeting those, all the way down through to feed into the software requirements. Each of those software requirements will represent a whole range of higher level requirements. Some of them will get tested at many levels. They can be tested all over the place. And then we need to certify the engine independently of the airframe. We actually demonstrate that engine is capable of flying before it ever gets flying, and the flight test requirements, those tests are either sort of taken on trust and closed out later, or independent of what we're doing to certify the engine. So, that was a bit of a rattle-stop tour. I probably haven't introduced anything amazingly surprising to you there. Our intelligence is not in the nature of the test. Each of those tests is generally fairly simple, but the whole program is complex. So where we have to put the intelligence is in managing it and making sure that all the software is tested and all the functionality is tested at the right vehicle at the right time. And we can't have teams of millions, and we can't have 8 spare engines sitting out the back, and we have to do it on time. And the really hard bit is you have to have commitment to complete the process. When you get near the end and you've got one test that you couldn't run because you couldn't simulate that part of the cockpit, but it's probably okay because it worked on the aircraft, so good, you can't certify. You've got to be able to prove it, and you've got to have management commitment to get the kit and the people and the time to do that. And it's no good having a commitment at the end. Commitment has to come from the beginning. You have to have a plan for certification and for proof from the beginning of the budget to generate the rigs and the tests and bring in the test houses and the test tools that we need. And then you'd arrive on holiday. And you won't have needed to worry about it after all. Questions?
One for £75 as well. Nigel.
Thank you. Just to reassure me, because there's some things I've never thought about when flying, what OS do you use, and what software language do you use, and why?
We generally use high-integrity operating systems like Green Hills. They have been certified to have effectively limited capability and really be constrained, and we can build on those. Languages, Ada is used a lot. We use C, C++. We have in the past used assembly languages like Lucol because the supplier, the hardware supplier, certifies with it. Why do we make those choices? Ada was very popular for a while because of its ability to really be proven well. C and C++ and things like that, because they come out nicely from model-based design tools like Simulink. We're using SCADE now. And when we used assembly languages, it can be hard to find a lot of people who can manage it, and the languages don't move on, and then you can't get the processes anymore. Does that help?
Thank you. How far up, you said you're using the results of model-based design. Are you going up and using the model-based design tools at the high level? It's sort of how integrated are you with that overall design? And the latest engine came out the year before last, I think.
Yeah, well,
so how far are you down the line with, or what stage of the process are you at with the new engines?
Well, XWB is being tested on the A350 at the moment, aiming for certification for the end of the summer. So that's the latest one there. That's flying around happily on the A350. We're fairly conservative. Are we really bang up to date? No. No, we don't slap stuff off and go, we'll come across this on the internet, it looked great, let's see if it works. We're a few years behind. We are using SCADE in some areas. We do use some higher level model-based design tools, Artisan, to a limited degree. We are still writing in Ada and handwriting code in areas as well, though, taking it bit by bit. You'll be pleased to know. We need to demonstrate things really work and are absolutely foolproof. Take them on.
You mentioned fault insertion. Presumably the code that supports that exists in a working engine.
Yes.
And does that not lead to any nasty little problems like security holes?
Sorry, do you mean fault insertion or sort of auto-generated within the code, effectively, like instrumented code?
Yeah.
No, that doesn't exist within the engine. Obviously, the instrumentation is all taken out. Fault insertion, where we have to instrument the code, that will be a different build, and then we'll have to take that out and run the functionality on uninstrumented code. We do fault insertion of by signal injection, so literally pulling wires out, sending the wrong type of values down the wires.
Right. Okay. I thought you might be doing it by software.
Yeah.
Right.
I don't think they'd let us do that.
If Nigel doesn't mind, I can feel my former colleague on my left and my colleagues at work urging me to add to what Nigel just said.
Please.
The ADA code is actually Spark subset and is subject to an amazing depth of static analysis for all sorts of properties before it goes to test, which is very important.
Yeah.
So it's very disciplined stuff, and I've seen it. So.
Yeah, thank you.
Last question.
Nigel, what percentage of defects do you find with static analysis, with a very comprehensive type of work you're doing on that, compared to dynamic testing?
That's a good question. We do find some problems with static analysis, and we clear those out fairly early on. So what we like to think of is sort of what percentage of problems get through to an engine test, if you like, and there the code level problems is just about nil. When we get to engine test, they're functional problems. They're things like if you open that valve and you're accelerating at a certain rate, then you get a funny pulse come out, and that causes the control laws to do the wrong thing because the design doesn't quite hang together. We get almost no code level errors get through to that sort of engine test. During code development, of course, yeah, we find code errors at times because that's part of writing code, and auto-generated code, very few. But where there's handwritten code, of course, there are mistakes. They're almost entirely eradicated. As near 100% as I think it's possible to get.
Okay, I think we've run out of questions. So thank you very much, Nigel. Thank you very much for your talk. Thank you.
Thank you.